In this video, I would like to show you how to use DLD-VISU to design a finite state machine. You log in like before and go to the digital logic design menu and select finite state machine. The design of finite state machines in DLD-VISU consists of 10 steps, starting with drawing the state diagram and ending with drawing the output circuits. You can choose between the more machine and the milli machine and use this area to edit your state diagram by activating the state button and placing as many states as you like, and then drawing the transitions between these states. So in a Moore machine, the state has two properties, which are the name of the state and the active outputs in that state. The transition has only one property, which is the transition condition. In a milli machine, the state has one property and the transition has two properties. So let's take a simple example, a vending machine with 4 states and 6 transitions. All the states and the transitions, and we can edit their properties. We call the first state 0, and the output signal, the only output signal is not active, so it is not open, and if the user enters $5 banknote, we go to the next state, which we call 5, and the output signal is still not active. Now we have edited all the properties and the state diagram is ready, and we can go to the next step, which is selecting the state code. So you can select binary code, one-hot code, or gray code, and you can assess yourself here by trying to enter the code by yourself, and some of them, not all of them, and then you see this is the correct code, the correct binary code. You entered one correctly, but the other one was not correct. It was corrected by the DLD-VISU. So, and as you can see, the code is now transferred to the state diagram, because from this step we will only work with the state code, not with the state names. So the next step is to generate the state table based on the modified state diagram. The state table specifies the next state and the output signals as functions of the current state and the input signals. Here again you have the chance to verify or to assess yourself by entering some values here. For instance, in this line we are in the state 00 and the user entered a $5 banknote, so we expect the next state to be this one here, which is 01, and the output signal is 0. In this line, for instance, we expect a transition from here to here, but let's assume that the user entered 11 as a next state instead of 10. The output signal is still 0, and if we verify, you see that you entered here the wrong value. So the other values which are produced without a background color, that means they are also not considered in the learning curve for self-assessment. So the next step is the design of the state memory. So the design of the state memory is straightforward. It just consists in selecting the flip-flop type. You can select between D flip-flop, JK flip-flop, and T flip-flop, whereas when you select JK flip-flop or T flip-flop, the progress charge gets some modification, because we have to derive the J and K equations, not the next state equations. So let's take the D flip-flop version and go ahead to the next step, which is deriving the state equations. And the state table is shown now in a little modified version, where the output signal is not shown here because it is not relevant to deriving the state equations. This is one of the principles in designing DLD-VISU, which is abstraction. So we should focus on the important or we should get the information which is relevant to the current design step only. So we can see that if you take the cursor to some one, the corresponding term in the equations is highlighted. So the next step is to minimize these equations, because otherwise the circuit would be too complicated, and this is done implicitly using the Quine-McCluskey algorithm. These are the minimized equations now, and the next step is to draw the input circuit. We already have the flip-flops, and we add the input circuit to them one by one. So the last three steps relate to designing the output logic, and here again the state table doesn't show the next state, just the output signal, which is very easy in this case. The output equations is just the end of the S1 and S0, in the state signals. So the minimization in step 9 would be redundant, and the output circuit is just an AND gate which is added to the previous circuit to get the complete finite state machine circuit. If we click on next step, we have the possibility to save this design in our history.